Welcome to the second part of the problem-solving session for Chapter 36. Let's begin where we left off. Question 7 says, a small fish is swimming 1 meter below the surface of the pond. What is the apparent depth of the fish as viewed by a child who is directly overhead? In part B, if the child is located 1 meter above the surface, what is the apparent location of the child above the surface of the water that the fish, this time, views the child? So let's begin with part A. Well, our expression for determining the apparent depth is Q, the location of the image, minus P, minus, because the image is going to be on the same side as the object, so in some sense it's like a virtual image, P, the actual location of the object, divided by N2, where the light is going to, divided by N1, where it's coming from. In the case of the fish viewing the child, N1 is equal to 1.33 because the light has to leave the water to enter to the air. Therefore, N2 is equal to 1. P, we're told, is the actual location of the child, 1 meter above the surface. So Q, in this case, is equal to -1 times 1 over 1.33. And so to the child, the fish appears to be minus 0.752 meters below the surface. So the fish appears to be closer to the surface than it actually is. And that you can see right there, that dot is where the fish appears to be to the child. In the second case, however, the light is traveling in the air, goes to the water, which is where the fish sees it, and the child is 1 meter above the surface. So the question is, where is the child located with respect to the surface? So here again, -1, but this time N2 is 1.33, and 1 is equal to 1. And so to the fish, the child appears to be 1.33 meters from the surface of the water. In other words, actually further than the child actually is. Next question. Suppose a converging lens, okay, so now we're working with lenses, has a focal length of plus 10 centimeters, and the plus here tells us that it's converging. Use the thin lens and magnification equations as well as ray diagrams to describe the image formed when the object is at the following distances. Well, let's take the first case where P is equal to 30 centimeters. Using the thin lens equation, we know that 1 over Q equals 1 over F, in other words, 1 over 10, minus 1 over P, 1 over 30, and common denominator here, 30, gives us 3 minus 1, or 2 over 30, so Q is equal to 15 centimeters. M is minus Q, or minus 15 centimeters, divided by P, which is 30, so the magnification is -1/2. Well, the positive Q tells us we're dealing with a real image, but in the case of lenses, a real image is on the opposite side of the lens as the object is. The negative tells us it's going to be inverted, and the half tells us it's going to be reduced. So a ray diagram for this would look the following. Here is our, actually we didn't need the vertical line, did we? Let's go ahead and just erase that. And let's take our principal axis, place our converging lens with 2 points to mark the foci of the lens. And because P is 30 and F is 10, our object is going to start out someplace over here. And of course, this isn't to scale, but we'll go ahead and just proceed anyhow. First principal ray parallel to the principal axis enters the lens and transmit passing through F. Second one goes through F, enters the lens, and transmits parallel to the principal axis. Third one passes through the center, and you can see roughly our intersection. Our C is a little bit off. This is hard to do with this pen, but essentially the image would be located here, where if you can see that if our ray through the center was a little higher, that would help us see our image. Well, it is inverted. It's a little difficult to tell that it's reduced to 1/2 size, but again, this is very rough, and it is real because it's in the opposite side to where the object is with respect to the lens. Okay, next part, B, P is equal to 10 centimeters. The lens equation tells us 1 over Q equals 1 over F, 1 over 10, minus 1 over P, 1 over 10. Well, that gives us 0, which implies Q is equal to infinity. We can't form an image because our object will be invisible. And so we can't proceed any further. C, P is equal to 5 centimeters. This time, 1 over Q equals 1 over 10 minus 1 over 5. Common denominator 10. 1 minus 2 is minus 1 over 10. And that gives us a Q, which is equal to negative 10. And that negative tells us we have a virtual image. Magnification equation, minus 10 divided by 5 gives us plus 2. The plus tells us we're upright. The 2 tells us we're enlarged. And now we try to form a ray diagram. Here's our lens. Here's our principal axis. Here are the 2 foci. Here is our object within the first focus and first principal ray. Parallel to the principal axis. And transmits through F, but because we know it's a virtual image, we are going to have to backtrace it because a virtual image forms on the same side as the object. Second one passes through the focus as though it's coming from the focus, so we angle it like this, and transmits parallel to the principal axis, and again we have to trace it back. Third one passes through the center, and again we have to backtrace it. Well, as you can see, although not a very well laid out picture, again because of our pen, we have our image forming roughly over here. So this was our object. It is enlarged, it is upright, and yes, it is virtual. Next equation, next question. Question number 9 tells us that we're dealing with a diverging lens, and it states to use the lens and the magnification as well as ray diagrams to describe the image formed at the following. So let's begin with the equations. P equals 30 centimeters. This time F is negative because we're dealing with a diverging lens. So 1 over Q equals 1 over F, or minus 1 over 10, the negative, because F is negative, minus 1 over P, well, that's just the 30 here, and common denominator 30, so we've got minus 3 minus 1 gives us minus 4 over 30. Q is equal to minus 30 over 4, which is equal to minus 7.5 centimeters. And of course, the negative tells us the image is virtual, but we know that in all cases of a diverging lens, that happens to be the case. M minus 7.5 divided by 30 gives us positive 0.25. Positive says it's upright. 0.25 tells us that it's reduced. What does the ray diagram look like? Well, let's come over here, and I went ahead and kept these so that we would be able to, let's see if there's any way we can enlarge this a little bit. I don't think that there's a way to grab this and enlarge it. Maybe there is. Let's move it down so we can see what the ray, again, we got to grab it somewhere here. Let's see if we can grab it like this. There we go. Oops. Not that, this. All right. So let's just erase this. And here's our object. First principal ray, parallel to the principal axis, strikes the mirror, and you can see the reflected ray back traces to the focus. So this is the, refracted ray, not reflected. This is the back tracing to the focus. Second one passes through from the object through, here we go, it's the purple one, from the object as if it's going through F2, but before it gets to F2, of course, it transmits, and then again we backtrace that transmitted ray. The third one through the center backtraces here, and so you can see our image is right over here. It has all the properties we stated. It is virtual. It's on the same side as the object. It's reduced, 0.25, and it's upright, positive. M is positive. Second case, P is equal to 10 centimeters. 1 over Q equals minus 1 over 10. Minus 1 over 10. Notice that this time the both have the same sign, so they're not going to add up to 0. In fact, they're going to add up to minus 2 over 10, which means Q is going to be equal to minus 5 centimeters. And this time we do get a diagram. Q is not at infinity. M is minus 5 divided by 10. We have an image which is upright and reduced to half size. Let's go ahead and see if we can locate that here. I'll just come over here, grab this thing, and see if we can go down and enlarge it. Oops. Let's grab it over here. Let's go a little further. See if we can make this a little bit bigger. So we can only go this way here when we enlarge it. So Here we go. Oops, seems to default to the pen. Let me go ahead and erase that. All right. Here we have first principal ray parallel to the principal axis, refracts so that the back tracing is through F1. Second one comes in as though it's going to F2, but transmits parallel to the principal axis, so it back traces parallel to the principal axis. The third one goes through the center, back traces through the center, and here is our image upright, reduced, and virtual. Last case, we had P was equal to 5 centimeters, and so 1 over Q equals minus 1 over 10 minus 1 over 5. Well, let's see, common denominator, 10 minus 1 minus 2 gives us minus 3 over 10, so Q equals minus 10 over 3, or minus 3.33 centimeters. Oops, seems like we've switched colors there. M is equal to minus 3.33 centimeters divided by 5. And that gives us a value of 0.667. Well, you can see that as we appear to get closer to the when we are within the focus, notice that the closer we appear to the lens, the bigger. See here, M was 0.5. Here, M is 0.667, and to start with, M was 0.25. So our magnification seems to be getting larger. Well, let's go ahead and see what we've got here. Sure enough, you can see the same rays. First one back traces to F1, second one back traces parallel, third one through the center, and notice that our image has gotten bigger. So in all cases of a diverging lens, the image is going to be virtual, upright, and reduced. Okay, last question. Here we have two converging lenses, and the first one has a value of F which is 10 centimeters. The second one has a value of F which is 20 centimeters. And you can see that actually there is a distance between them which is 20 centimeters, and what that means is that the focal length of the second one happens to be right at the center of the first one. So not only is the focal length of the second one 20 centimeters, they're separated by 20 centimeters. We place an object, this time we're going to label P1 for the object distance to lens 1, and of course P2 would be the object distance to lens 2. Q1 is the image distance due to F1, so the first lens. Q2 is the image distance due to the second one. And let's see, before we actually work out our numbers, I'd like to go ahead and grab this image here and enlarge it so we can get a sense for, it's easier to do it this way than for me to draw it, because my ability to draw with this pen is somewhat limited. But I can trace it this way for you. So here is our object. We label it as O1. Here is our first lens. Here is our second lens. And of course, we recall that the distance between them is 20 centimeters. All right. First principal ray parallel to the principal axis and refracts through F1, and F1 would be 10. So this distance right here, as you can see from here to here, is 10 centimeters. But we proceed onward, so I'll go ahead and just erase that so we don't end up with too much writing on there. Second one comes in through F1, located right here, and transmits parallel to the principal axis. Third one goes through the center, and there it is. Well, this is the intersection of those transmitted rays, which we're calling I1. Now, we will find, once we do a calculation, that I1 should, according to this diagram, be equal to 15 centimeters. Well, because this is 15 centimeters, you can see that P2, that's this distance right here, P2 should be equal to 5 centimeters, and in fact, we'll verify that. So now we're going to use our I1, the image that is formed by lens 1, becomes the object for lens 2 at a distance of 5 centimeters. So here we go, parallel to the principal axis, through the focus, and back traces, so you can see we're going to end up with a virtual image. Second one comes in as though it's coming from F2, and parallel to the principal axis, there's back tracing to that one. And the third one would go through the center, although they didn't show us, and back trace through the center. Well, that intersection there gives us I2, and I2, we are told, is 6.67 centimeters. Well, that would be Q2. Because it's on the same side as the lens, we should expect it to be negative 6.67. Well, let's go ahead and work it out numerically now that we've examined the ray diagram. We start off with P1 is 30 centimeters. 1 over Q1 equals 1 over F, 1 over 10, minus 1 over P1, 1 over 30, and we end up with 2 over 30, so Q1 is equal to 15 centimeters, just as we expected. Well, because Q1 is equal to 15 centimeters, and there's 20 centimeters between the two lenses, it must be that P2 is equal to 20 centimeters minus Q1, minus 15, which is 5 centimeters. And sure enough, that's what we had stated earlier based on the diagram. Let's go ahead and obtain M1. M1 is minus Q1 minus 15 divided by P1, 30, and this gives us minus a half, which means we're inverted and reduced from the original object. Well, let's see if we can obtain 1 over Q2 is 1 over F2, 1 over 20, minus 1 over P2, which is 5 centimeters. And that gives us negative 3 over 20, which means Q2 then, once we take the reciprocal, minus 6.67. So it is virtual, it's on the same side as the object, but the object is the image that lens 1 formed. M2 is equal to minus Q2, or minus 6.67, divided by P2, which is 20, P2, which is 5 centimeters, and that gives us an M2, which is 1.33. Well, that tells us that the image formed by lens 2 is upright with respect to the object, but don't forget that the object itself in front of lens 2 was upside down, so the image is also upside down, so these are upright with respect to each other. Now, to get the total magnification, we take the product of M1 with M2, and of course that is going to give us minus a half for M1 times 1.33, and that gives us a magnification which is minus 0.667 altogether. Well, this minus here tells us that the image is inverted with respect to the real object, in other words, the object in front of lens 1, and the 0.667 tells us that it's reduced with respect to the object, and you can see here, here's the object. Sure enough, the final image is reduced, inverted, but real. It is real since it is on the opposite side of lens number 1. It is real for lens number 1, but inverted for lens number 2, since it's in the same side as the object that was in front of lens 2. Well, this concludes the problem-solving session for Chapter 36. Until next